First, I will go over the requirements for project 2. Okay, I hope everybody already go over all the requirements in the project, uh, the 16-bit risk-based target set. Because this time I will try to write I will try to use script language to write a small app, and then it will automatically grade your project. So please follow all the requirements as what we wrote here. Okay. The first, to simplify the project, we remove unnecessary instructions and only keep this 14. Okay. As you said, we separate all the instructions to three parts. The first part is load and store. Definitely, at the beginning, when you start a simulation, all the registers should be 0, nothing inside. The first thing you need to do is to load some value from your memory and into your register. You have 8 registers from R0 to R7. Also, in your data memory, we fixed the number is also 8. I finished that part of programming for the memory. So you can see it here. For example, the partially code I provide for the data memory. At the beginning, there's a file, the name is test data inside the test folder. You will see that. And all the data inside is for your data memory. When you start the simulation, it will automatically read all the values from this file into this memory. Memory is your data memory variable. And then how can we read your project? We will only check your memory, the final state of your memory. Because every time, if your memory there's any value change, because after you load, you need to run some instruction, and then you need to write back. So after write back, definitely the value in the data memory has to be changed. Every time, if data memory, the data change, it will automatically print out all these things into a new file. Okay? This is the only thing we need to use to read your project. So try to make sure that file can be created automatically. Okay. This is the file name. You can change the file name into your UBIT name from the parameter file. I used to define all the parameters in a separate file. Okay, here you have separate file name. If another thing is, it's a group project, but if you really want to do it individually, you can do it. This is the final file you should name. Okay, and here's the simulation time. Because you make for different people, maybe you need 1,000 nanoseconds, maybe somebody use 10 nanoseconds to finish all the simulation. So make sure we change this value according to your design. And we fix this value, the row of how many rows for the data memory. So there's only 8 rows in your data memory. But how many rows for instruction memory you can change it? Because you really need a lot of instruction to verify your design is correct. So you can change the number and also add different instructions inside your program. This is for your instruction memory. The first one is for data memory. Here, I show some examples. Definitely you need to add more. First, you load some value from R0 to from memory to register, and then load another value to register, and then add them together. At last, write back. That's the way we will verify your design. Okay. Here it is. We have all the requirements, load store, and all these parts they can be done in the LU. So it looks there's a lot, but in fact, when you do the project, it's only one line of your program. It's very simple. And there's a little bit different for the group project and individual project. If you want to group Okay, you have to do all of them, include how many distance is first. Another one is detect the overflow problem. Overflow, like you have two numbers. Both of them are very large. For example, 111 plus another 111. So overflow will happen after you add them. In this case, you need to provide an actual register to show, okay, after I add them, there's an overflow happening. That's it. You don't have to, that's enough. You don't have to resolve the problem. You just need to detect the problem. Like a warning, that's enough. Okay? This is the only difference between the group project and individual. Group, you have to do these two. Individual, you don't have to do these two. Okay? And here, I already separated for different bits, which bit represents which part. The first bit, 4 bit, will represent for OP. So it's an add, or it's a subtract, it's a load, or store. Okay? Because we only have 14 different instructions, so 4 bit is more than enough. And the second part, usually I use to represent the RS1 is register 1. The third one is RS2, but for the case of store, it will represent WS. WS, you have these two numbers. Okay, RS1 is the address for register, first register. RS2 is the address for second register. WS, when you write back, you also need to provide the address. All this, this diagram I totally copied from Professor Wanyel's lecture. I think 99% of the component you have to do it yourself. Maybe you can change one or two small things, remove them because they are not necessary. You can follow this data path, but you don't have to. If you feel, okay, your idea is much better, you don't have to use it. But just make sure every time if you run this, this is the one for you to run simulation. The name is the task, and the live is 16-bit. You cannot change it because everybody will use the same one. After the simulation, after your design, you need to use this to do simulation and automatically create a file inside the test folder. Okay, it's the output of your data memory. Okay, here at least how to get full marks, 100 points. Be careful, you have to follow all them because nobody will grade it. Only computer will grade it automatically. Let's see. Okay, here's the, okay, one more thing. If you go to Piazza today, I update a little bit things here. Last time when we posted the project 2, I asked you to maybe want to start it. If there's any bug, please let us know. But until today, nobody mentioned anything. But today I find there's a little bit mistake. It's here. In our class, every time it's PC plus 4, right? It's the PC equal to PC plus 4. That's because every time PC will plus 4 bytes. It's a 32-bit instruction, so every time you will plus 4 bytes. But in our design is 16 bit, so it should change PC equal to PC plus 2, not PC plus 4. Okay, that's the difference. So it's the same case to the branch. Every time you should plus 2 at first and then plus outside. Okay, here's the smaller update we did today. And then, okay, here it is. Okay, for your final project, normally, if let me do it, I will, for example, this will be your top level module. Okay, inside your top level module, there's nothing else. Only data path unit and the control unit. Because the first data path is the whole diagram. You have to finish all the components, each as one module, and then connect them. That's what you need to do in your data path unit. And how about control unit? Because only connect them together is you will find the circuit doesn't work. You have to use control unit to control each component. When should you start? Like, for example, when should you start the PC? When should you start this one? When should you start that one? It should be a flowchart diagram inside your control unit. Okay, it's a state diagram inside your control unit. Okay. For the data path, that part maybe is not that difficult because like those only the this ALU is just one line for each instruction and the marks and these are only the register and memory. Everything is there and to connect them is also not a problem. The most challenging part comes from your control unit. You have to design, okay, the sequence, the state for each one of them. And let me show you an example about the stage. Okay. A good thing is for this kind of projects, there's a lot of similar results. You can Google online, just for example, but for sure you cannot direct copy from those code. But if you really don't know how to do it, you can try to find this result I found online. It's about the state diagram. Okay, start from PC equal to 0 at the beginning, and then for each state, you name them as S0, S1, S2, S3, and then go back like that. This part you have to read and understand by yourself, and then you can start all project. Definitely for this topic, this is very different. You cannot do that because here is the schematic. I cannot say schematic, but it is summary. Here you can see we have data path unit, not control unit. There's a lot of signals the control unit will control what data path should do. Okay. So next, do you have any question about this?
Where is the reset signal in our
reset signal you can set it yourself. You can all the signals you can add. Just make sure after you run it, there's auto fail and be great. And also another thing is as what I said, this is a top level module, right? But you really don't have to follow it. If you feel, okay, I don't like it, I want to write all the code inside one module, that's fine, remove it. And then, sure, you can do it. This way maybe will make you feel a little bit confused, but finally you will find this kind of way to program will make your design much easier. Because you don't have to separate the control and data unit. It's not a good way, but it's also acceptable. But just to make sure every time the same thing, you need to leave out the cell.
So can we change the import of the top module?
Top module, I don't suggest to change it because everybody needs to use this one, right? This is a test bench, it's fixed. Because it's really unnecessary to give any other input. One clock is enough.
So can we add the reset signal here?
Reset signal here?
Yeah.
If you change that, you have to change the test bench.
Yeah.
Right.
How can we know we are going to load our first instruction?
How can we know?
Yeah.
When I did that, I do it automatically, like without any signal. If you start simulation, you start to load all the values. But
So the first pulse age of the clock is start. Can we?
Okay, deal. If you feel okay, the start button is necessary, you can add it.
Okay.
I'm sure without start button you can also to do simulation, but if you like this, please add button. That's fine. Okay. Any other question? Ron?
So for this project, we would need to provide the bit file, the bit string file.
No, this time you don't have to download the board, so bit file is not necessary.
So the input won't be, we will have to consider that the input will be from the FPGA, so it's going to be manual input. We will
No, what
It's
do
a
you
lot
mean input?
of
Because
it's a lot.
the input for this project
like 30, 40
is only
hours.
these two files. One is the data memory, one is the structure memory.
Oh.
And another
You don't
input
need
is
the
clock.
board for this.
Clock is already there in the test bench, so there's no other input you need. And one more thing I have to say is here.
Let's start with it on Monday.
See,
Monday between 12 and
every time if you want to load something from the memory to the register, you have to go to, for example, some register at first, and then this register plus offset, and then put this value as the address of memory, and go to this address of memory, fetch the data, and put it into WS its position. So that means the IS1 cannot be unknown, right? It has to be 0. So I ask everybody, when you design your register, the first thing is to initialize all your 8 register, the value as 0. This cannot be unknown. Okay.
this with the nervous things.
Any other question? No? Anybody want to do it individually? Or you want to? Okay, that's fine. Because the maybe the way to grade you guys is different from others. So I need to write different script. That's fine. Any other questions? No question. If you have any question, you can ask me after the class.
So we suggest everyone starts through this project as soon as possible. Actually, you should already start it. It cannot be done in one day. No way.
What about 2 days?